My name is Frank, and today I'll be going over how to do CS170 Homework 3, Question 6. So this problem is about implementing the FFT algorithm in Python. And the first thing we need to code is this FFT function, which takes as input a list of coefficients, okay, for our polynomial of interest, as well as a list of the roots of unity at which we want to evaluate our polynomial, okay? So now recall that FFT is a divide and conquer procedure. So we need to make recursive calls to FFT within the FFT function itself, right? So recall from lecture that these are the recurrences that are used in FFT, right? In order to evaluate our polynomial A at all the nth roots of unity, right? And notice that we split into like AE and AO, which represent like the even and odd coefficients for our original polynomial, okay? So even evals is simply going to be a recursive call to FFT, okay, but passing in every other coefficient, right? And by passing in every other coefficient, I'm only passing in the even coefficients into my even recursive call, okay? And similarly, for the odd evals, I'm also going to pass in every other coefficient, but starting from the coefficient at index 1, right? And in doing so, I only pass in the odd coefficients from my original polynomial, okay? Now I'll also need to pass in a list of roots into my calls to FFT, right? And recall that if I start with wanting to evaluate my polynomial at the 2nth roots of unity, then I need to pass in a list of the nth roots of unity, right? Because the 2nth roots of unity squared are basically the nth roots of unity. And so to help you visualize what I should pass in for the nth roots of unity, I draw a small toy example here for the 8th roots of unity, right? So you notice that I drew out 8 bread points along the unit circle, and they're evenly spaced around the unit circle. Those are the 8th roots of unity, okay? And what I was circling now in green are the 4th roots of unity, right? Which are basically 4 points evenly spaced around the unit circle. So what you can see here is that given the 2nth roots of unity evenly spaced out around a unit circle, the nth roots of unity are simply every other 2nth root of unity, okay? So going back to the code, right? If I just pass in every other root of unity, I will basically get my original list of roots of unity squared, okay? So that's why I just pass in every other root of unity as inputs to this recursive call to FFT, okay? Now finally, in this last line over here, result, I need to basically combine the results of my recursive calls and return my original polynomial evaluated at those two endpoints, okay? Now I'm going to route the answer first and then explain the logic behind the answer in a second, okay? So this will be even evals. Okay, I'm gonna change this to this. All right, so what I just did here was I was simply calling my recurrence that I was provided, right? We provide this recurrence where if I want to evaluate my original polynomial A at a root of unity omega, I just need to plug in omega squared into AE and omega squared into AO, right? So that's why I've like called even evals here and odd evals here, right? And this plus or minus roots I is basically the omega value, okay? Now, the other critical thing I need to mention here, oh wait, I'm forgetting a parenthesis over here. But I was going to say the other critical thing I want to mention here is why can't I just go ahead and add these two lists and know that the resulting values are in the proper order? Well, the reason is because I'm going to tell you this right now, is that whenever I negate a root of unity, it is simply going to be located 180 degrees away on the unit circle. Okay, so what I mean by that is like for this root of unity, let's say I call it omega 1, right? That negated is located over here, 180 degrees away on the unit circle. And for this omega 2, its negation is located 180 degrees away from it on the unit circle. Same for omega 3, 180 degrees away on unit circle. Okay, that's the idea, but why is that the case, right? Let me show you why that's the case mathematically, right? So if I have a root of unity omega, right, you might recall that the generic formula for a root of unity is given by e to the 2 pi over n times I k for some natural number k, right? That's a generic formula for root of unity. Now, if I'm interested in finding out the value of negative omega, that's simply negative 1 times e to the 2 pi over n I k, right? And what you should memorize or know by now is e to the pi I is equivalent to negative 1. So in case you didn't know that, that's a good formula to memorize, okay? So e to the pi I, so this is equivalent to e to the pi I times e to the 2 pi over n I k. And since exponents add together, whenever I do whenever I do exponent multiplication, basically what this shows is that whenever I negate a root of unity, its negation is going to be located pi radians away from it on the unit circle. Okay, and just getting back to code, that is why I can just add together the list. I can add together like this list plus that list because I want to evaluate my polynomial at all the roots of unity, right? So this first list over here, evaluates my polynomial at all the roots of unity that are above the x-axis, okay? And my second list, which is the one down here, is going to evaluate my polynomial at all the roots of unity that are below the x-axis over here, okay? And I know that I will be returning all my values in the proper order because of that property which I just mentioned earlier about how negative omega is simply located pi radians away from positive omega on the unit circle, okay? So that is part one. See you in part two. Hi, everyone. So now that we've covered part one, let's cover part two of this assignment, right? So basically here, we want to fill out a function that calculates the nth root of unity, okay? So the first thing we need to fill out, right, is theta n. So theta n is basically where on a unit circle is the nth root of unity located. And that's simply given by 2 pi over n. Now, why is that the case? The simple reason is that we know that the nth roots of unity are all evenly spaced around the unit circle. And so, since the unit circle is 2 pi radians, the first nth root of unity is going to be located at angle 2 pi over n, okay? And if you look over here, I drew out like the complex plane to illustrate that, right? So if omega is my root of unity over here, I want to point out that cosine of theta, right, is equal to x over 1, this diagram. Notice that the radius is 1 because this is a unit circle, right? And similarly, sine of theta is equal to y over 1. Okay, so what you're asking us to do here in this calc nth root function, right, is return a representation of this nth root of unity in terms of its location on the x-axis and its location on the y-axis, right? And so we just saw right now that the x component, the horizontal component of this root of unity is simply given by math.cosine of theta n. And similarly, the vertical component along the y-axis is given by math.sine of theta n, okay? So that was relatively straightforward. We were just converting our nth root of unity into its representation in terms of its location on the x-axis and its location on the y-axis, okay? Now, finally, we just need to put this all together and fill in the function for actually multiplying the polynomials, right? You notice in this function, we start with two inputs, cof1, which are basically the coefficients of the first polynomial, and cof2, which are the coefficients of the second polynomial. And we want to multiply these two polynomials together. And briefly overview of how we're going to do that, right, is we're going to convert both polynomials from coefficient representation into value representation using FFT. Then we'll take the pairwise product of these polynomials and finally convert the value representation of the product polynomial back into the coefficient representation of the polynomial of the product polynomial and return that as a result. Okay. So let's start with the basics, right? First, I'm going to fill out target degree. Okay. And what I wrote here in the notes is that target degree is basically the smallest power of 2 that's greater than or equal to the degree of the product polynomial plus 1. Okay, I'll explain why plus 1 in a minute, but let me just write this down first, okay? So target degree is going to be given by len of cos 1, whoops, minus 1. Now, len of cos 1 minus 1 is basically the degree of polynomial number 1, right? Like, for example, if cos 1 is a list of 3 elements, then know that this is like a degree 2 polynomial. Similarly, this will give to me the degree of polynomial 2, right? Okay. And normally, remember when we do polynomial multiplication, that the degree of the product polynomial is simply the sum of the degrees of the input polynomials, right? Like, for example, x squared times x cubed is x to the fifth. You just add the exponents, right? So the degree of the product polynomial here is also simply the degree of polynomial 1 plus the degree of polynomial 2. But I need to add an extra plus 1 over here. And why is that the case? That's because, as you might remember from CS170, right? If I give you a polynomial that has degree n, it is determined by its value at n plus 1 points, right? So I need to add an extra plus 1 here to account for the fact that in order to determine a polynomial of degree n, I need to evaluate at one extra point, one more point than just n, okay? So that's going to be, oh, sorry, I also forgot to mention. So that is the value of our, that's the number of points we want to represent. We want to calculate our polynomial at, but we also need to add in one thing over here, and it is to call our helper function next power of 2. Right, so what next power of 2 will do is it will take that, the degree of the product polynomial plus 1 and round it up to next power of 2, okay? Because we're always like passing in a number of roots of unity that is a power of 2, okay? So now the next line of roots, this is just to create like the list of the roots of unity, right? And we have a helper function for that. It's called calc all nth roots, and I pass in target degree, okay? So how this works is like, for example, if target degree is 32, calc all nth roots of 32 will return to me a list of 32 elements, and those will be like the 32 roots of unity around the unit circle. Okay. All right, cool. So now when you fill out, so now this product is actually going to like convert like our coefficients of our polynomials into their value representations. And you might recall that we can do so using the FFT, right? So what we'll pass in is coefs1. So that polynomial evaluated all the roots we have available to us. And evals 2 is the second polynomial. Again, evaluated all the roots that are provided to us. Okay. And now that we have our two polynomials in their value representation, we can take their pairwise products. Okay. So this is like the actual multiplication part, right? So I'm like multiplying E1 times E2 for E1, E2 in zip evals 1, evals 2. Okay, so this is the actual multiplication of the two polynomials. Now, finally, I now have the value representation of our product polynomial. I just need to convert it back into the coefficient representation and return that, right? And you might recall that the way we do so is by multiplying by the inverse van der Waals matrix, doing the inverse FFT procedure, right? And I wrote the inverse van der Waals matrix up here, okay? You might recall that this matrix times the standard van der Waals matrix equals the identity matrix. Okay, this is from the textbook. All right, so my inverse roots, okay, I'm basically going to calculate the list of omega to the negative 1, right? So that's simply r to the negative 1 for r in roots, right? I just took my list of roots from earlier and just inverted all of them, okay, by raising them to negative 1 power, which is the same as taking the transpose of that complex number, okay? All right, And finally, res coefs. So this is basically the result coefficients, right? Okay, so that is done through an inverse FFT procedure. So I'm going to call my FFT procedure again, but this time, instead of passing in coefficients, I'm passing in the value representation for my product polynomial, which is given by product evals. Okay, and I want to evaluate those product evals at the inverse roots. Okay, so that is the inverse FFT. That is like equivalent to multiplying by the inverse Feynman matrix, okay? With just one more tweak, and that's this. Yeah, so let's set up a list comprehension here, and that's to say that like for all the elements returned by the inverse FFT, I have to divide it by the target degree. And that's like this part over here, right? Divided by n. So that's like the extra adjustment factor I need to do. I need to divide it by n or divide by target degree in order to get the final accurate list of coefficients, okay? So that's all there is to problem 6. If you go ahead and plug in all these inputs into a Jupyter Notebook and run the rest of the cells, you should get all the expected outputs, okay? So thank you for listening.